Hello and welcome everyone to our webinar tonight on calculus. I'm being joined by a good friend of mine, Stephen Julian, over in Perth, and together we're going to be presenting a whole host of things on, focused on calculus. So let's just see if we've got Stephen there. You there, Stephen?
Good evening, everyone. Can you hear me, Peter?
Yes, we can. You're coming through loud and clear, and I can see the list of attendees is building ever so quickly. So I'm not going to waste a lot of time at the start because we have an enormous amount of stuff to get through. Stephen and I were experimenting just before the webinar, and man, it's a big call to get through it all tonight, but we're going to make a shot. So without any further ado, what I'm going to do is show you an example of the sorts of files that you can find out on the web. Now, I don't profess to be able to build something as fancy as this, not without any rest, at least for the next 6 months, but you can download them from the web. So this is a sort of calculus problem. This is more of a teacher demonstration file that you can share with students. So it's our traditional volume of a box type problem. So we've got our flat pack. Courtesy of IKEA, we can strip it apart and fold it up very quickly. I don't think anyone's built an IKEA box that quick, but there we go. And of course we can change this value of A, which is the size of the cutout, and on the right hand side we're also seeing how that's affecting the overall volume of the box. And the person that made this, of course, probably had to show off a little bit because you can tilt your box and have a look at it from various angles. You can even change the original height, width, length of the box and start to generalize. So there's a lot of stuff in some of these documents. I think that's a wonderful demonstration of the power of Nspire and how we can get a lot of ideas across very quickly. But we're going to start with something a lot simpler. This is a document that I've built up. It's in the attached files when you register for the webinar. It will also be on our website. You should be able to download that as early as tomorrow, but we can send links out to it following the webinar. So the first thing that I try and get students to do when we're looking at gradient of a function or starting to think about things like the gradient function is starting off with the first principles, but not literally first principles, thinking about the sorts of stuff they would already know from previous years, and that is the gradient of a straight line. And in this case, we're not actually measuring the gradient. All we're looking at is to say, is it positive, negative, or zero? Also talking about the fact that a tangent is a line that shares the gradient, or shares the same gradient of the function at that point. So at this point here, this tangent has the same gradient as the curve. Now, I don't go into the details on how the calculator's doing that. Just needless to say, we're collecting information such as the gradient is negative, and then eventually it gets down to zero gradient, and then it goes positive. And the worksheet that accompanies this has the students filling it in just with plus signs, minus signs, and zeros to signify the signed value of the gradient. So it's the sort of thing that we assume, or hopefully can assume, that students know whether that gradient is positive, negative, or zero. If they don't know that, then there's a bit of work to be done. On the next page of this activity, students can then do the same thing, but obviously with a cubic function. So we're seeing exactly the same sort of information, but we also see the reason why we can't say something like a tangent just touches the curve but does not cross it, because right now the tangent is going through the curve because it's at the point of inflection. And gradient's still negative, zero, positive. So again, students are just doing a signed table, and in the next part of the activity it suggests that they draw these other ones. There's no tools to help them, but they could draw it on a piece of paper. I still use pen and paper techniques, and follow it around with a pencil and do the same sort of thing. Determine whether gradient's positive, negative, or zero. After that, in the activity, the students come along and through the magic of technology, and this is something we certainly couldn't have done without the technology, is an actual numerical value is assigned to the tangent. And when I say we couldn't do it without technology, not accurately anyway in terms of the students just drawing a tangent and estimating or measuring that way. And in this case, you'll see that P jumps in whole number increments, and in the activity, the students actually populate a table of values, the same as what they would have been populating in, say, Year 9 or 10 when they're trying to graph a function. So the idea is we have a set of gradients for all of these different values of x. So the fact that we have or can produce a table of values suggests that there might be some sort of a rule or function that describes our gradient. Similar sort of one, just a slightly different curve, but following the same idea, and the students again populate a table of values. And then in the third step, we're doing a bit more for the students. This time, the table of values is automatically being generated and graphed at the same time. So we're introducing one little component each time we move through the activity. So in this case, the students can see that these points form a straight line, and they may or should be able to figure out the equation to that straight line. They could hypothesize and say, I think it's 2x or x, and they might say, well, that wasn't close enough, maybe it's up a little bit, and see that the gradient of that function is 2x by 1. So they can test these sorts of ideas. And of course, you'd expect there to be similar ones. There's one where the gradient comes out with a different equation. Had to do a sad parabola, as my students would call it. And the last part is an opportunity to investigate. So it's more open-ended in this case. So we have a quadratic function where the students can just grab the turning point and move it around and see how the gradient function is associated with this quadratic. And the question on the actual worksheet itself is open-ended like that. Find the sorts of patterns and observations that you've got. For example, we've also got down here, you can see the gradient equation is being produced at the same time the quadratic is, and students should notice that a vertical translation is not impacting the gradient function in any way, and that really the only thing that's changing in our quadratic is this last term down here, the constant on the end, and that is not having any impact on our gradient function. The other bit that's kind of cool is if we translate the graph horizontally, that the gradient function moves along with it. Now later on, of course, that's something students can see when they start looking at things like the chain rule. An f of x plus h type of approach. So that's the activity. You can download that from our website. It's in the files that come along with this webinar, so it's not something you have to create. All the questions and indeed all the suggested answers are in those files, including this TI-Nspire file that's there. So what I'm going to do now is I'm going to transfer across to Stephen, my co-presenter tonight, and he's going to show you an exam, or where you'd go next if you were teaching calculus for students just starting calculus. So I'll transfer over to Stephen, and while we're just waiting for Stephen to share his desktop, there's a few questions that have come in, and I'll try and answer those as quickly as possible. And perfect, we're now seeing your screen, Stephen, so you're good to go.
Thank you, Peter. Good evening again, everyone. And I've actually noticed there's a few Western Australian names that I recognise, and a few people, obviously, that I know. So I hope you're all having a great evening.
Sorry, Stephen, your screen, there it is. It just took a while.
Oh, sorry.
Computer. That's all right.
All good?
Yep, all good.
Okay, thanks, Peter. The first part that I'm going to look at tonight is pretty much a notes page or a connected file that will take you through, and for the students to actually spend some time looking at connections with the idea of particularly first principles, but also getting into looking at other connections. And the idea of this file is that they can type in a rule or an equation, and it changes everything within the file. So the whole document is actually linked. And the idea would be, particularly with, again, your higher kids who would be doing calculus, is for them to explore a little bit for themselves. You'd obviously have to go through some of the concepts of first principle and lead them through it, but you'd hope that they'd also be able to pick up some of the patterns themselves. So just going into 1.2, and this document again will also, if it hasn't already been made available to you, will be made available to you. So the first part of this TNS file or this document is looking at first principles and the limiting chord idea. So in 1.3, it goes through and looks at the fact that we've got an entry box. And now I'll leave it how it is for the moment, but hopefully you should be able to see that I've just gone into that math box and we've got the function 5x cubed. So the idea would be that the students can explore different functions, and anything that they enter in here will then be affected in every other screen across the document, and there's 17 screens in total. So it actually gets into a fair bit of detail about what's going on within with the ideas of calculus and differentiation. So we'll leave it for the moment as being 5x cubed, so I'll just click out of that box. On the next screen, it actually takes the kids through, or the students through, the idea of first principles. So if I go into 1.4, this screen discusses the idea that we're looking at horizontal distance, so we're looking at our what's usually called the H value, that we're not going to have 0 to start with, so if the distance between the two coordinates horizontally is not 0, then we should have two distinct points. Down lower on the page, it talks about the idea that we have the H value, we can define it and change it, which I'll show you in a moment. And then it also goes on and says we can pick whatever our first X value is. So if you want to get the students to see that this is changing along a particular curve or get them to explore things, you can actually get them to manually change the values for that part. I guess an important part with this whole document, which I've highlighted a number of times when I wrote it, is you need to make sure the students think about if things aren't looking how they should be, the good old Windows Zoom settings, that they may need to play around with that. Okay, so we'll move on to page 1.5. So here we have our original function, which was our 5x cubed function. We have our H value, which for this first illustration is 1 unit wide, and we're getting our chord. So the students can see that between 1,5 and 2,40 for the original function, we're forming a chord that's cutting through those two points. If I go back to 1.4, what the students can do is change and get them to see that as we make that H value smaller, the chord should get closer to relating to what the original curve looks like. So I'll just change that to 0.5, click on that. Nothing appears to have changed yet on that screen, apart from the H value. But if we go now onto our graph screen, you'll now notice that the chord is getting considerably closer to relating to the curve. The X values and Y values are automatically changing, so that, again, the students, as they change the H value, can see that's happening. I guess the one thing, if you're going to use this with your students or if you're using it yourself, I have found, and it's something I'm hoping to come out with a version 2 of this, is that if you drag the point, it can start affecting some of the links between the variables. So I would be encouraging your students and yourself to be changing the H value and the distance on this screen, 1.4, rather than doing it on the 1.5 page. So again, you're better off getting them to think about the H value from that screen and not from the graph itself. Okay, so I'll go back to 1.4 and just change that, but I just wanted to show you that it will link. The same thing will happen if you change the X value, but I won't do that. You can have a play around with that yourself if you would like to. So I've changed the H value now back to 1. If I come back to our original graph, again, the students can see that change, what's actually happening. All right, now if we move on to 1.6, to find the gradient of the tangent, so now we're actually talking about first principles. It actually explains to them the idea of H approaching 0, that the 2 points are getting so close together that we can assume that the horizontal distance is pretty much 0. It's almost an identical point. And at this stage, you could start to really talk about the idea of tangents. 1.7, and this is where this file could be used not only to illustrate the students, but again, if you're thinking about down the track for an exam notes page that can actually help the students see the connections. How you use this is obviously up to you, but you'll notice here that I've got step 1, and this will actually take the students step by step through the whole first principles concept. It tells them what the first step should be. It tells them that the f of x plus h will be that given the function we started with, and the f of x part. So all they need to know is that the two parts are being rearranged and rechanged to be the appropriate function. Moving on, and I won't bore you with this because I think it's hopefully pretty self-explanatory, but you'll notice that next page it now has expanded the whole function of f of x plus h. So now it's looked at the idea of substituting the x plus h in. Again, it's told the students what they should write down. They should hopefully now see that there's some kind of connection happening here with their expansions with polynomials, and they've actually also got the original function again given to them to remind them that they must take away that value or that function. The next page, now it's actually simplified it for them. So again, the students start seeing, well, now we've got that. Now we need to try to write it where the f of x plus h, take the f of x, is actually simplified. So again, the students have been given everything that they need there. And again, depending on whether you're using this as an assessment helping tool or whether you're using it as a way of illustrating, the students can see the connections at this stage. Moving on to step 4 and pretty much the last step. On the last two steps, now it's actually giving the students what the whole of the equation, the fraction inside the bracket is become once it's all been factorised and simplified. Obviously the little asterisk here is just telling them to be careful that there could be some division of 0 going on, so there may be some issues with restricted domains and things like that they need to be just mindful of when they're actually working with this. For a normal polynomial, obviously that won't be an issue, but when you start getting into some of the other things, you obviously could be finding that they need to be a little bit more careful. And then at the very bottom of the page, it gives them the final connection. So what you'd hope, again, the students would see there is that they know that they can see that that's what the final derivative function is, and they can actually make the connections and start seeing some things that might be going on. I might go back to 1.1, or 1.3, sorry, just to quickly show you what would happen if I did change that to be a square, for instance. So again, I've just come back to the original document, clicked on that. Again, nothing amazing happens on that screen, but if we now go into the 1.5, you'll now notice that that's automatically changed it to a parabola. The chord has been changed appropriately so that it's actually now got a totally new function. And I'll just quickly flip through. Again, you'll notice that the first page of step 1 is being changed to be appropriate, so it's now 5x squared. It's now got the right substitution. And I'll just quickly go to the last page here. Now on the last page, again, the students can see that the final answer is 10x. So the students have had a chance to play around. You could start them with x squared like you would normally do with first principles and get them to explore. So they can actually start seeing what the connection is rather than us necessarily having, as teachers, giving it to them spoon-fed. Now, again, I might just go back and change that to the original function. Sorry about this. Okay, so I've changed it back to 5x cubed. If we now move to the end of the first principles part, the next section is graphs of the derivative function. So now we've got the students understanding the idea of first principles. Now we can actually lead them through and look at the first derivative and second derivative, and hopefully the students again can start making a few connections themselves about that the first derivative is talking about gradient and the second derivative is talking about concavity. Now again, you'll notice that the function is changing automatically, so we have 5x cubed in grey, and that's probably going to need to be changed a little bit. That was coming up better than this the other day, but 15x squared in grey, and then the second derivative we've got 30x in red. So again, if they change on that first page, all of those first, second derivatives will also change. On the next page, we now have the graphs. So clearly for the students, they can see the original function f of x. They've got the graph in grey of the second derivative, sorry, the first derivative. So again, the students can actually start seeing that, okay, well that's a cubic, this is a parabola. So maybe there's a connection there. And then finally, and I've written on the previous screen again, they may need to fiddle around with their view windows a little bit, the window zoom, just to make sure that they can see things a little bit clearer. But in this case, they can see that there is a line forming there. So the first function was a cubic, the derivative was a quadratic, and then we've got a straight line for the second derivative. We could lead them into quartics and start seeing if they can see the connection. Okay, the last part of this notes page gets into the idea of equations of the tangent to a function. So now what they can do is start playing around with the idea of, well, we know that this point is getting closer and closer to a zero in terms of its horizontal distance. So now we can think about the idea of the equation to the tangent and what that might be. And again, for them to explore and see if they can start seeing some connections and working out some shortcuts. So on page 115, to find the equation of the tangent, now again, this x value can actually be changed to being something like x equals 1. They could actually change this again to whatever the question or whatever questions you want them to look at. The gradient of the tangent is given when x is substituted in. Again, this is automatically coming from that earlier page. The question then goes on and talks about, well, the gradient is 15. Can we see why that's the case? So again, they can try to look back at the equation they got earlier for the derivative and think about, well, it was 15x squared. We're putting in 1. Could there be some kind of connection there? And then finally, it gives them the equation of the tangent. And again, the idea of trying to say, well, we've now got an x value. How, if we've got a gradient, how could we then find the c plus c value and hopefully drag on some of their knowledge from year 10 and earlier? Just as a matter of interest, before we look at the last two pages, the way I've set up this, the tangent equation is actually using the idea of a tangent line feature, which is in the menu, and you can actually get it from the calculus parts. So here we've got tangent line, the function, and the substitution of the x value that they change up higher on the screen. And then finally, the part that does appear for them, if they're not interested in how this is created, is the 15x take 10. And you'll notice if I click outside that box, we get the equation rather than seeing all that extra stuff being shown. On 116, now this is again leading into the very last part where they now have the idea that they've got the chord to be pretty much a tangent. They've got the original equation. We're talking about a value of x value of 1. We've now got our h value, so it's so close to 0, it's a tangent line. We've been given the equation of the tangent. Let's now look at what it actually looks like. So if we move on to the last page, we now have our equation, so our original blue equation, which was the y equals 5x cubed. We have our tangent line, and the students can actually see the idea of, okay, that's the point 1. If I put 1 into the original y function, we'll find that the y value is 5, and they can start seeing that there's a connection there. And again, obviously, if they've gone through and changed the original function, they can start seeing some connections. So I might just quickly do that. For people who aren't aware, Control Up can give me all the documents in one go. So I'm going to come back to the 1.3 screen, change that to be squared, Control Up, and then if we come back to that last page, again, the students can start making some connections. Now we have our quadratic. We have, in this case, it's actually turning out to be a very similar line. It's going through 1,5. But again, the students can actually see, linking with all the other screens that they've been using, that we actually now have our tangent line and we're starting to make some kind of connections with gradients, which I think would lead pretty nicely into Peter's next part, where he's actually going to start looking at special functions and the idea of equations. So again, hopefully that file, which will be available to you, will be of some use to you in the future. Okay, thank you, Peter.
All right, thank you, Stephen. So as a precursor to what I'm about to demonstrate, we're assuming that students have gone through and done some derivatives of polynomial functions and the like, and then we start to introduce what I'd like to call a special function. And in this particular case, what we've got is a flexible line, and the gradient of each little line segment is being plotted using these points along this dotted line. So in other words, if I make this point here move up, you'll see as that little line segment here gets steeper, then its gradient becomes more positive. Now, my question or challenge to the students is, can you, and if we look at it from a simplistic point of view, can you make it so that that dotted line sits on top of the solid line? Or, thinking that in a more mathematical sense, is there such a function whereby when you differentiate it, find its gradient, that you'll actually return the same function? So by experimenting with this little flexible line tool, we can see we can gradually align that dotted line sitting quite nicely. Yes, it's segmented. It's not a continuous line in that context. They're just chunks. But it allows us to focus on little sections of the line and what it would look like if we put those points closer and closer together. Now you can see there, I'm just about topped off the screen. So if we start from the other end and build it, the other thing that teachers may be surprised at here, and I know doing it with teachers in the past, the students aren't surprised that perhaps there's more than one function which satisfies this condition, well, at least more than one equation. I think I might be on shaky ground if I said more than one function. So I'm just going to bring these lines down a little bit. And you can see that we're getting pretty close to having the problem solved. And it looks remarkably like an exponential. Oh, but we haven't done exponentials quite that way yet. So let's have a look at it. Maybe it's a polynomial. We don't know what degree that polynomial is. So we'll start with one that's really, really big. And we'll work towards finding what that polynomial might be. So let's suppose the original function goes through the point 0, 1. Now we choose x equals 0 for a very important reason, and that is if I substitute 0 into my function, the only thing that's going to be left is this term a0 on the very end of it. But since I said the gradient of my function is the same as the original function, then that means that p dashed of x equals p of x. So p dashed of 0 will also equal 1. And therefore p double dashed of 0 will equal 1, and so on, forever. So let's see. Here's one I prepared earlier. I've already defined the function. So let's start with p of 0 equals 1. And that tells us that a0 equals 1. So now I've defined it. The second thing that we knew is that the derivative of our function, that is this one here. Now I can't put the 0 in there because otherwise it'll substitute 0 and say, well, that's a constant, the derivative equals 0. So I need to say the derivative equals 1 given x equals 0. That's my way of substituting once it's finished. And I see a1, that was the coefficient of x to the power of 1, is also equal to 1. Could be a coincidence. If we're getting a pattern here, maybe they're all 1s. Let's try another one and see what happens. So we'll grab our second derivative. In other words, p double dashed of x equals 1 given x equals 0. So now we're seeing that they're not all 1s, that they're slightly different. Now, just for convenience sake, and because I'm working the phone with one hand and the calculator with the other, I'm just cheating a little bit here. So we'll say a2 is a half. Let's jump back up here, and through the wonderful copy and paste feature we have, then we can see that a3 is 1/6. So we'll drop that in as defined, and we can go again. Now, of course, students won't go through this quite as quickly as what I am. It's an investigation. It's designed to take a good hour of a lesson. So we'll divide that one by 24, and hopefully teachers that have not seen this before will be starting to see, hopefully, a pattern in those coefficients. If you haven't, we'll do one more just to convince you of such things. Oops, divided by 120. Now if I type in what my p of x looks like so far, I went all the way up to 6, so let's just do one more, shall we? We're slightly ahead of time, so I can do that. And if you didn't see the pattern before, now you will. So now we've got P of X. Now we could keep going. We could keep going theoretically forever. And what would the derivative of that thing look like? And it looks remarkably similar, only this power drops off. The 6 will come down the front. We'll get x to the 5 over 120. That one will become x to the 4 over 24. That term will, and so we're only doing the derivative of a polynomial. And if we wanted to graph that thing, let's see if I left a graph page there. There it is. And if I changed my window settings, I would see a curve that looked a little bit like the one I had before, but it picks up. Well, this is a polynomial of degree 6, so we kind of expected it to turn its nose up down the other end there somewhere. If it's heading off in this direction, then it's going to turn back up somewhere. So we would need to keep on going to get a better approximation of what the real curve looks like that goes on forever and ever. So we replace that with a continuous function, and that is an exponential function rather, and we can change the base until we get that dotted line sitting pretty much on top. So it seems to be between 2.7 and 2.8. In fact, if I went back to that previous page and wondered what would that base look like, P of 1, there, I probably want it approximate, 2.718. Hopefully that number's starting to look a bit more familiar to people. So of course, yes, it's e to the x, but it's a way of actually coming up with our Taylor polynomial, and if people haven't seen, you can actually bring up the Taylor polynomial. It doesn't matter if they're not on your course, because this is a nice way of doing an investigation and getting the kids to actually understand, rather than just learning by definition that the derivative of e to the x is e to the x. They've got some understanding sitting behind it. So that's that investigation. Now, I won't go through the entire part of this one. This one's putting a square peg in a round hole, I've titled it. So if I go up to the top, and this looks similar to the exponential one, so if you're thinking about what could I do as an investigation later on this year in calculus, you can cover the exponential one in class, because this one follows along a similar line. There's a bit of extra stuff in it. So you can do the exponential one in class and then set this one as a homework task or an assessment task. And the good thing is you don't have to figure out the answers, because the answers are all done for you as well. So there's a few little scaffolding questions at the start here just to get the kids warmed up. And it says, I wonder if we could model, say for example, sine x as a function, could we model it by a quadratic? What would that look like and how close could it be? So, oh, look at that. There's a sine x graph. That was handy. So if I want it to cross through the x-axis at the same points as my sine x graph, then dare I say it'd be x times x minus pi. Well, to save us some time, we know that it's going to be upside down, so let's do that. That's not a very good approximation, and if I want it to pass through this turning point here, so that aligns, you can work out the coefficient. Turns out to be 4 over pi squared, and it actually aligns quite well. How well? It needs to be measurable, and the activity does ask students to measure. I won't call it a wellness of fit, because I'm sure there's a better term. I just can't think of one at the moment. So I'm going to change my trace step, and I'm going to set that as pi on 18. The other thing that Stephen and I are both using version 4 of our software, and that allows you to type exact values in. You may have noticed that I've got pi on 4 here and 2 pi and so on. When you go into the Windows settings, you can specify those and they come out nicely. So if I trace, oops, I don't want to just trace one of them. As a comparison, I want to trace all the graphs that are on my screen at the moment. And as we move along, you can see as a quadratic, the values it's estimating are not too bad. It's pretty close to 1 decimal place accuracy. Granted, we'd want a little bit more than that, but it's not too bad, particularly the endpoints. We're pretty much spot on there, and obviously at naught, we get a couple of spots where we're exactly correct. So then the question sheet says, what if, having done that one, what if we modeled it with a cubic function? And why wouldn't you use a cubic function? The idea getting the kids to think about the fact that the turning point's no longer in the middle. So then they look at a quartic function, which, if you don't know, actually models it extraordinarily well, at least over that small domain, and asks the questions, well, if we wanted to just model it over a small domain, could we indeed work out any other trigonometric value? And as the question here hints, it's almost accurate to 3 decimal places. And looking at some of the names on our webinar tonight, perhaps most of them were using trig tables when they went through school, and would recall that they were only done to 4 decimal places. So therefore a quartic bringing out 3 decimal places is not too bad at all. Where this activity then becomes similar to the previous one is we say, well, what if the first derivative equals 1 when x is 0, the second derivative is 0, then -1, then 0, and then it cycles through. So could you then go ahead and figure out all of these coefficients? And the students come up with the Taylor polynomial for sin x, and they can very similarly deduce the Taylor polynomial for cos x, and even talk about, if they really want to stretch it, why don't we have a Taylor polynomial for tan x, and coming out that we only get a rational function, we don't actually get a polynomial. So you can ramp that up to a much higher level and push it into year 12. One of the other reasons why I like to do these sorts of investigations with students, other than just the black box treatment of a calculator, is we're actually pushing the understanding. And if the students are doing complex numbers, the idea of how do we show that e to the I theta is the same as cis theta format. In Victoria, certainly we talk about modulus and argument form, and that can take on either of those two. So there's a lot of connections that you can bring out in that activity. So we can see that we've gone from differentiating basic polynomials to a much higher level, and looked at, let's call them some special functions. So now I'm going to pass back to Stephen, who's going to demonstrate how we might solve some typical calculus type questions using TI-Nspire. And he's got some nice questions there. So I'll pass it back to you, Stephen.
Okay, thank you, Peter. I'll just check this time. My screen's coming up okay?
Yeah, it takes it. Yeah, there it is. Perfect.
There.
Well done.
Fantastic. Thank you for that, Peter. Okay, the next part I'm going to look at is 2 exam-type questions that would be typically given to students under exam conditions in particularly Year 12, but also Year 11, and looking at how we can use the power of the CAS calculator to do some of the calculation steps and also do some comparison things with the students. The first question I'm going to look at is going to show you the power of particularly solving simultaneous equations. If you're like me, usually I tend to stick to your basic linear functions, and we're generally looking at 2 unknowns, which in this question we will be. But looking at things now that are maybe a little bit more complex for the students and may save them a little bit of time, and again, to get them to be thinking about the connections more clearly than just going through rote learning and step-by-step equations. So I'll look at the first question, which is for the function, and again, this is a pretty standard type of exam question, often comes up in both non-calculator and calculator-assumed sections. For the function y equals 3x cubed plus px squared plus, plus px squared plus q, getting a bit late here, I was starting to see too many p's on the page, where p and q are constants, dy dx, so the gradient is 16, and the point is -2, 0. By calculating the values of p and q, determine an equation for y in terms of x. So one of those kind of questions where obviously the students would have to go through, do some work, set up some simultaneous equations, and then use their knowledge to solve and come up with the final solutions. So what I've done on 1.3 is I've actually looked at the traditional approach. So a way of going through and what I've called the paper and pen method. I guess there's probably other ways of calling it, but we've looked at the idea that normally we'd put in -2 into the function, we'd simplify it and come up with something that would be some kind of simultaneous equation, equation 1. And so that's using the knowledge of -2 being the x and 0 being the y. And then simplified it and got it to an equation. And again, I've just typed this in. This is actually on a notes page, so I haven't done anything miraculously with the technology here. This is a straight typed up notes page. The next line, so the students have thought, well, coming back to the question, we've used the fact that negative 2, 0 is important information. Now the students have to think about, well, what's this useful? The dy dx equals 16. Is there something that means? Well, as I always say to my students, when you see a question like this, at least differentiate. You're going to get at least 1 mark, and hopefully maybe a few more, but at least 1 mark out of the question. So coming back to 1.3, we have our differentiation, which again, I've just typed this in manually. They've then got to think, well, at x equals negative 2, we have our connection, so negative 2, we put it into our derivative function, and we then simplify, and we can find that p equals 5. The students will go, okay, well, we've got p equals 5. We can come back up to equation 1, which is 4p plus q equals 24. They'd then substitute that in and get their answer, q equals 4, and they'd have their answer. Obviously, a lot of very, very good mathematics in there, and you'd hope that your students, they will need to know that for the non-calculator section. But if they suddenly got hit with a question like this, or if you wanted them to, again, get some practice quickly and try to see if they can see some connections happening with the values and how it's being generated, what I'm going to look at now is on 1.4, I've just set up a calculator page. And I'm going to use the power of the define function and simultaneous equations to have a look at how we could do exactly the same question but have the calculator basically generate the values for us. And again, hopefully then the students can make the connection and see how they're using this. So I'm going to start with defining our function. So we've got define. I'm going to call it f of x. And we had the original question 3x cubed. Now this is probably an important stage here where you say to the students that they need to be mindful of when they need to be using multiplication between numbers and pronumerals and when maybe they don't. Obviously for the next part, which was p x squared, we definitely are going to need a multiplication there, otherwise the calculator will interpret it as being px as being the variable. So we've got px squared plus q. So now the students have got their define, and if we type enter, we'll actually find that the calculator has now got that as done. It actually understands that as being something that we've stored. So next thing the students need to think about is that, well, we're obviously going to have 2 unknowns. We will end up having 2 equations that we'll have set up, but rather than going through and doing it by paper and pen, how could we actually use the technology to come up with those answers? So the next step would be to go into menu. And if they go into menu and then use algebra, so our normal steps number 3 for algebra, we're going to go into solving a system of equations, so number 7. Now because this is obviously not going to just be linear equations, we're going to have other things that we're going to be working with here, so I'm going to type number 1 for solve system of equations. The number of equations will be 2. If I tap down, now I'm not looking for x and y, I'm actually looking for p and q. So remembering to put a comma between the 2, and again, good little exercise for the students to realise that they can change things so that it doesn't have to be just x and y. Okay, so now we have our template for our simultaneous equations. So the next thing we want to do, and now we've defined the function, the beauty of this is we don't have to retype the whole thing in. We can actually use f of x as being the function we're working with. So in the first template box, I'm going to put f, and you'll notice it's coming up as being bold. So yes, it's definitely recognising that's a defined function. Our point was x being negative 2, and it was giving us an answer of 0. So that's our coordinate value. The function, when negative 2 is being put in for x, we're getting 0 as our answer. Okay, moving down to the second box with our template, we can now think about, well, what else have we been given? We've been given that there's a derivative at negative 2, 0, and the gradient at that point is 16. So what do the students need to think about? They need to think about how can we now set this up as something as a simultaneous equation. Well, the shortcut, which I think we've mentioned earlier, if you push shift and then the minus sign or the subtraction sign, you actually get your template for differentiation. So very nice, very quick. We don't have to go looking for it anywhere else. In the first box, I'm going to put x because that's what we're differentiating with respect to. Even though we're finding p and q, we're still doing normal differentiation. Now, in the next template box, we're just going to type in f of x. So we're still going to differentiate with respect to x the function f of x. Now you'll notice I've just moved outside of the first closed bracket. We want that to be equal to 16. That is our gradient for the particular point that we're now looking at. So we're differentiating, we're making it equal to 16. But we also need to tell the calculator that we're actually using the point x equals -2. So let's go up to control, go to our given sign, and we're looking at x equaling -2. All right, so going through those steps again, very important to be very careful with your brackets here. I know even when I first was playing around with this, occasionally putting the 16 inside this bracket. So be very, very careful that the students know where things have to go. So we've now got our d dx, we've got our values, we've got our x equals -2, and if we hit return, we get p equals 5 and q equals 4. So the students can see, well, the original function up above was this. We're just going to replace it with 5 and 4. And if we come back to the original page, you'll actually notice that that was the two values that we had, 5 and 4, using the traditional paper and pen method. So the thing that the students would now need to think about is, what would they write down? Well, the final step would be f of x, or sorry, y equals, sorry, because the original function was y. So y equals 3x cubed plus 5x squared plus 4. The question was asking, back on 1.2, by calculating the values, determine an equation for y in terms of x. So the final answer has to be in terms of what they've been asked. So it wouldn't just be p equals 5 and q equals 4. They need to make sure they give the answer appropriately. So that's one thing that you can actually do, and just again showing a few little shortcuts that you can use. The second exam question that often comes up, and another thing that also particularly can be a bit challenging to show in class, I've already touched upon in my notes page in the first activity the idea of showing first and second derivatives. Another common question that can come up in exams is this one. Sketch y equals x take 3, x take 2, x plus 1. Then using this graph, sketch the graphs of dy dx and the second derivative. Comment on the meaning of these graphs in respect to y equals, etc. So now we're looking at the connection between the first and second derivatives and how that can all link in together. Again, over here in Western Australia, quite common that students will get given a graph and then taking that graph, looking at the various versions of derivatives. Particularly now with the new national curriculum, I'm pretty sure that's going to be, well, I know it's pretty common over East as well. So how can we now use the power of the TI to get the students to see these connections and get them prepared to be thinking about the right steps through this kind of question? So I've already created a graphs page on 2.2. What I am going to do is I'm going to make this into a split screen, but I'm going to not be quite as creative as I did with the notes page. I'm just going to split this into two screens, one above the other. So doc, number 5 for page layout, number 2 for select layout, and I'm going to pick number 3, layout number 3. So a horizontal split. So we get something looking like this. Now I'm going to get them to we're going to create a new graphs page down the bottom, so I'm just going to make sure that the bottom is highlighted, and then I'm going to add a graphs page. So now we have a horizontal comparison, and the thing I like about this is, as we do with students when we teach this idea, we try to get them to line up everything so they can see clearly what's happening and where the key points are going to be occurring. So coming back up to the top. Now the graph that we were actually going to enter was x take 3, x take 2, and x plus 1. I've picked one that actually works nicely with the view window sizes, but obviously again you might have to talk to your students about window zoom and how they can fix things up. So if I now press enter, there's our original function. Now obviously the key points that we want students to eventually be looking at are the maximum, minimum, and the points of inflection, and then see how concavity and gradient change might be being affected by this particular graph, and then how that connects with the first and second derivatives. So in menu, I'm just going to go through and quickly find out the key points. So analyze graph number 6. I'm going to find the first value, which was the maximum, so number 3. Just find our lower boundary and our upper boundary, and then I might just grab that text and move it across. So I'm hoping most people at this stage would be familiar with how to get the maximum and minimums. Then again, as I said, same thing with the minimum, lower and upper, and we've now got our minimum point. And the other one we'll need to work out, particularly for the concavity change with the second derivative, is the idea of where the point of inflection is. So menu, analyze graph, number 5 for inflection. Just go a bit below it, a bit above it, and we now have our values. So particularly for this activity, we could obviously explore a few other things, but they would be the main things we'd be wanting to look for the first and second derivatives. Okay, I'm now going to come down to the bottom graph, and we're going to look at a few things. So you'll notice it's still recognising F1. Now we want to find the second derivative. Now this is again something that's very powerful. Not sure how many teachers have played around with the idea of graphing a derivative function, but we can actually use our shift minus key. There is template options as well, which I'll show you for the second derivative in a moment. But we can actually, using shift minus, we actually now have our template again for the derivative. We're looking at x. If we go inside the bracket, we want to find the first derivative of the original function. Now this is a good chance for you to talk to the students about the fact that they don't need to type the whole function in. It's now got it memorised, so if we put F1, again it goes bold, so we can clearly see that the graph is still being recognised. X, so the calculator still remembers that we're talking about x as the variable, and if I graph it, we now have our first derivative function. And again, very nicely it appears, and the students can sort of see we've gone from some kind of cubic to a parabola of some sorts. Now, I must admit, sometimes for my own students, I'll create a new graph page for this next step so that they can actually look at the first derivative separately to the second derivative. But it is obviously a very powerful tool for the students to be able to see everything on the same screen. So before I do that, actually, I might just quickly find, again, some of those key points. So what we do want to do is make sure the students think, well, hey, we've got the maximum up here. Oh, we've got an x-intercept down here. Let's just see what might be actually occurring. So menu, analyze graph, we're doing zeros, so number 1. If I now focus on that first 0. Oh, now that's interesting. We've now got that the x values are the same for our turning point and our x-intercept with the first derivative graph. Let's do the same thing for the second one, so 0 for the x-intercept, lower and higher. And now hopefully the students are starting to see, oh gee, well, yep, we can clearly see that that point there, 2.54 on the original graph for x, is matching up to what the x-intercept is on the second graph, and same thing on this point here. Now we'd probably also be wanting to say to the students, well, what about the point of inflection? What can we think about there? So if we just drag the picture up so we can actually see that. Oops, I'll just grab the label, that's handy. Okay, so now we'd want to say, well, this point's now looking like it might be lining up. So maybe we should find this minimum point on our new graph and see whether it's giving us the same x value as our point of inflection. So menu, analyze graph. We're looking at a minimum on our new graph. And lo and behold, yes, we're getting the same x value. So hopefully now the students are seeing very clearly that those things are lining up. The next thing we'd want the students to think about, depending on which course we're teaching calculus to, is how can we look at the connection of the second derivative? So while I've got the second page still highlighted, tab, now there's a whole heap of ways of doing this. We can actually find the derivative of the derivative, which I'll just quickly show you how to do that. Shift, subtract, x, and then I could go inside and do shift, subtract, and so we're finding the derivative of the derivative. That would be one way of doing it. The second way we could do it, I'll show you probably the best way in a moment, shift minus, and because the first derivative is function 2, we could actually say, well, function 2. And so the students would get the derivative of the derivative function, in other words, the second derivative. So there's two ways, and I've actually found that with my students, sometimes they remember that idea better than thinking, well, there's a template and let's find it. But obviously we want students to have different tools in terms of when they're doing this, to have an opportunity to remember it the best way they can remember it. So I'm going to go actually and use the template little box, which is next to the 9. If we come down to the bottom here, I think Peter used this a little bit earlier, we actually have this spot here, and this can be used in the graphs page as well. So if I click on that, we now have our derivative. I can change that to the second derivative. So we've now got the second derivative of x. Because we're now finding the second derivative, I do want to go back to the original function, which was f1. So I'm doing the second derivative of the original function. If I press enter, lo and behold, we now have our line. So now the students again are seeing all on the same screen, cubic, we have a quadratic, and we have the line for the second derivative. So I guess the final thing now we want the students to be able to make the connection is, well, what might be the most important part? What do the below the x-axis and the above the x-axis parts mean? And I didn't touch on that earlier, but talking to teachers, again, the idea of the first derivative being above the x-axis and the first derivative being below, and they can see where the gradient's increasing, decreasing, etc. So now they can actually say, well, what's this point? What does the line below the x-axis mean? What does it mean if it's above? So if we go to menu, analyze graph 0, whoops, we need to pick the graph we're interested in, go below, go above, and it's starting to get a little bit cluttered here, and that's why I do often keep it to two different graph pages. But the students, and hopefully you guys can see here, that was the new point. Our x-intercept is 1.33, which happens to correspond to the turning point of the first derivative and the point of inflection of the second derivative. What they also should hopefully now see is there's our concave down on the original graph. On this side, we've got our concave up. That point there is our new x-intercept, so the second derivative equal to 0. Our concave up is everything to the right of that point. Our concave down is on the left-hand side of that. And hopefully, again, the students can also see the connections with the first derivative as well. So, yeah, just a couple of little tricks in there, particularly the idea of using first and second derivatives within a graphs page. And obviously, going back to my first exam question was the idea of using simultaneous equations, but in probably not a traditional way that most of us probably usually do them. So anyway, hopefully that's made a lot of sense, or if it hasn't, sorry. But anyway, I will now pass you back over to Peter, and I'll let him wrap up what we're doing today. So thank you, everyone.
All right, thanks, Stephen. Now, the last thing, and some people sort of say, oh, there's not enough time to do data logging in maths classes, but with only about 4 or 5 minutes to go, probably closer to the 4 minutes, I want to try and demonstrate that these things can be done. Now, hopefully what you're seeing on the screen now, yes, is some fishing floats. Now, I actually have, strangely enough, one of those on my desk here, and I will try and demonstrate. They cost anywhere between $10 and $15. They make a beautiful obstacle to put in front of a motion detector. They've already got a hole pre-drilled in them, so it actually makes a much better pendulum than some of the makeshift things that I used to do. So what I'm going to do now is just go onto an open document. Where are we? Just a blank document, and I'm going to plug the motion detector in to my computer. It's exactly the same as if you'd plug it into the calculator, and you can see it's starting to measure position. Now, just bear with me. I'll just put the phone down, and I'm going to record this pendulum swinging in front of the motion detector. You may think, what on earth has this got to do with calculus? But a lot of courses actually have use of motion to introduce the idea of rates of change. So I'll hit start and I'll record this pendulum swinging in. This is live, so if it doesn't work out first go, I'll see if I can get it a second. So bear with me. All right, so that's our pendulum. As you can see, it's not too bad a sine curve or cosine curve. So what I'm going to do is change my graph type to a scatter plot, and we'll bring up our variables, and they're nicely named. We'll put time on the independent or x-axis, and we'll put position on the y-axis, and it might be worthwhile just zooming in on that data. So we can see we've got something that looks remarkably like, as I said, a sine or cosine curve. I do like to show the x-axis in this image, so we can shrink our graph down just a little bit, drag the screen around until we expose our x-axis a bit more. That's pretty good, because it gives the students a sense of the actual practical context of this question. Now, the next thing I'm going to do, and teachers can decide whether they want to do this manually with students, or whether they just want them to use some sort of a regression, I'm going to type in a weird value like 0.5, and you'll see why in just a moment, because I want to see what would that horizontal translation, a vertical translation of that function look like. It's about 0.4, something in cos x plus 0.4. Let's start with that. Cos x plus 0.4. Looks like the amplitude's too big, so let's drag that up to here. And 0.62 down to 0.4, something in the amplitude of that would be about 0.2, see how good my memory was, 0.22 when we just typed that in, and that's not too bad. It looks as though it might have been just a fraction bigger. I can't stand being a little bit off, so let's change it to 0.23 and see how that fits. It's not too bad. We can now get rid of that line. I don't need it anymore. And we might start to think about, well, is it perfectly aligned there? Well, we can do a quick trace. And I'll just zoom along here. I've used a cosine curve so I can locate the top of that function. We can see it's translated horizontally about 1.65. So let's do that. Minus 1.65. So now we're getting somewhere. Looks like my first amplitude might have been better, but anyway, we'll bear with that. And that was 0.65. Let's just do another trace. Where are we? Trace. And we'll go along until we find the next maximum value, which appears to be about 3.3, and the other one was 0.65. We'll just introduce a calculator page, because running on the fly, I'm not even going to attempt to do those sorts of problems in my head. So 3.3 minus 0.65, and we get 2.65. How many of those will we see in 2 pi? 2.37 of them, so let's go back and edit our function just a little bit. 2.37. I think I did that upside down. Let's change that a little bit. Oops. The good thing here is, of course, the students are getting feedback as they're typing this in, so it's a valuable experience for them, if nothing else. Oops, too far. Let's try 3.1. That's not too bad. We're getting there. So we can get a reasonably accurate graph. I'm not happy with that. We could have gone a lot better than that. Let's try 3.2. 3.2. That's a little bit too much, isn't it? Oh, I see what my problem is. My brackets are in the wrong spot. Let's go back. No, they're not. They're looking good. A little bit off. So the idea here is, once your students have got the equation, then the calculator actually recorded, let's change to scatter plot, the calculator also recorded the velocity time. So once they get an equation for, once they get an equation for their position time, then they can use that same information, going crazy here because I'm trying to do two things at once. That's operate a phone, well, three things: operate a phone, talk, and press buttons on a calculator. So let's do velocity, and we'll need to zoom out a little bit to get an idea on what that looks like. And once the students actually, and I might just hide some of those labels because they're getting the page a little bit messy. Hide that one. The students can see that these maximum points here align with x-intercepts of the velocity. So when the pendulum reaches its outermost position, it stops momentarily. And as it swings back through, as it passes through the bottom point, it reaches its maximum speed down here, and it swings back through and reaches another maximum speed. We can also talk about the direction that it's traveling. So there's a lot of practical things that students can connect with that. One of the really good ones is the fact that it doesn't matter where the motion detector is placed in terms of the velocity of the function, or the velocity of the pendulum, but it does alter what my position time graph would look like, because the further away the pendulum is when I'm swinging it, the further that's going to translate that function upwards. But from a practical context, we can see and understand that the velocity time graph will be completely unexpected. Oh, there we go. Somebody's just told me what I did wrong with my function. Let's just change it. That was Mr. Neil Woods has noted. There it is. He spotted that very well. It's 3.2 or 3.1, not 3 times 2. So that's looking a little bit better, isn't it? 3.2, getting there. So I think I just did exactly the same thing. No, it's all right. So that gives you some idea how you can use a motion detector to help study calculus. The other one which works out really cool, and I've demonstrated at workshops before, is get a really big party balloon, 1 metre in diameter, put the motion detector in front of it, let it deflate, and you have a graph of dr/dt, and you ask the students to work out what is the change in volume with respect to time, and therefore the students can do the appropriate by-hand calculus to do that one. Now, I'm afraid we're out of time now. I hope everybody got something out of tonight's webinar. There's a couple of people noted that I did times instead of point. Thank you for everyone's comment. And hopefully everybody has finished writing their reports, and maybe that's why we've got so many people joining us tonight. And hopefully parent-teacher interviews are off next term, not this term. Thanks everyone for joining us, and thanks Stephen for all your work tonight too.
Thank you, Peter, and good night everyone. I hope your reports and everything else goes well. So thank you.